Hello, my name is Federico Corradi and I'm a senior scientist at IMEC in the Netherlands. Today I will present a small survey on radar perception for autonomous unmanned aerial vehicle. This survey has been written together with Professor Francesco Fioranelli from the Technical University of Delft. The outline for this presentation is the following. I will first introduce the problem. I will then introduce the principle of operations of radars and signal processing. I will then showcase some important examples of radar perceptions on board of UAV or drones, and I will conclude with some discussions and outlook. Let's start with the introduction. Today, we have several societal challenges in energy, agriculture, transportation, logistics, and in smart cities. Drones have already been deployed in several of these use cases. However, their use is limited by the need for human operation and control. Nevertheless, drones can perform air operations that manned aircraft struggle with, and their use brings significant economic savings and environmental benefit while reducing the risk to human life. However, to scale up the services and move beyond human operations, it is required to enhance the safety and autonomy of drones by developing safety-critical systems that can be realized by exploiting several sensors modalities. We need to strengthen the perceptions of drones with robust sensory systems, with increased sensory resolution, field of view, multi-sensory systems that combine artificial intelligence routines on board of drones to improve their safety and autonomy. For these reasons, drones' advanced perception will benefit from radar sensor and onboard computing strategies. Radar are ideal for improving navigation while enabling faster and safer decision-making. Radars can measure distance, speed, angle of arrival, and can be used to classify different targets. Radar are complementary modalities to cameras and lidars, which both work in the visible spectrum and slightly beyond it. In particular, lidar can measure distance, speed, and motion direction. However, lidars and cameras are both limited by lighting condition and weather condition, and in addition, the use of sonar sensor is mainly limited in low-speed scenarios like in parking assistance on motor car and in autonomous landing in drones. On the other hand, radars work well in the gigahertz frequency band, and millimeter wave radars offer high integration, low cost, high resolution, and are ideal to be integrated in small drone low-cost platforms. But how do millimeter wave radars work? In the following few slides, I will introduce the principle of operations on the frequency modulated continuous wave radars and their signal processing strategies. As previously mentioned, radar can measure the distance, speed, and angle of arrival of multiple targets. I will now introduce the FMCW radar operation, the concept of IF signal and IF bandwidth, and the range resolution. An FMCW radar transmits a signal called a chirp. A chirp is a sinusoid wave whose frequency increases linearly over time. You see here on the left a plot in which we have amplitude and time, and the chirp is depicted. Common radar carrier frequencies are also listed here below. Those are frequencies that one can usually find in commercial radar platforms. A chirp is characterized by start frequency f0, a bandwidth b, and a duration TDC. The slope s of the chirp defines the speed at which the chirp ramps up. In this case, with a bandwidth of 4 GHz, it ramps up in 40 microseconds. The chirp is ramping with a slope of 100 MHz per microsecond. We will see that the slope and the bandwidth are very important parameters that define the system performance. The simplest FMCW radar contains a single transmitter and a single receiver antenna. A synthesizer generates a chirp, and the chirp is transmitted by the TX antenna. The chirp is then reflected by a target, and it is captured by the receiving antenna. Importantly, the RX and TX signal are mixed together and the resulting signal is called IF signal in the mixer. The mixer has two important properties. The first one is that the output instantaneous frequency is equal to the difference of the two input instantaneous frequencies, and the output phase is equal to the difference of the phase of the two input waves. These are very important properties of the mixer. For this reason, the received signal Rx is a delayed version of the transmit signal, in which tau here is the round-trip delay. Since the frequency of the signal at the mixer output is the difference of the instantaneous frequency of the TX chirp and the RX chirp, it results in a straight line. This means that a single object in front of the radar will produce an IF signal that is a constant frequency tone, also called bit frequency. Importantly, the frequency tone S tau is equal to the slope 2 times the distance over the speed of light. This is because tau here is 2 times the distance over the speed of light. In the case of multiple objects or target in front of the radar, a frequency spectrum of the IF signal will reveal multiple peaks, as it can be seen in this picture. The range resolution of a radar is the ability to resolve two closed space targets, which comes in the form of two peaks in the frequency spectrum. Intuitively, one needs to increase the IF signal to increase the bandwidth to have a better resolution. And the table here below shows some typical bandwidths for some off-the-shelf FMCW radar with the specific range resolutions. One can directly observe that larger the bandwidth, the more range resolution it is available. In fact, 4 GHz bandwidth gives a range resolution of 3.75 centimeters, while a 600 MHz bandwidth gives a range resolution of 25 centimeters. Modern FMCW radars come in the form of tiny systems on chip with antennas integrated usually in the PCB. For example, on the right you can see a picture of IMEC 79 GHz radar system. This radar has a range of 30 meters, a range resolution of 7.5 centimeters, can measure objects up to 50 kilometers per hour, and with a velocity resolution with 1 km per hour and a latency of only 10 milliseconds. In summary, a system-on-chip radar is composed of several components. First of all, an analog RF front-end contains a synthesizer that generates the chirp. One or multiple mixers send the output to an analog baseband processing systems, which then send the output to ADC that converts the IF signal into a digital stream of bits. Finally, digital signal processing systems, DSP, uses these bits to perform signal processing as FFTs, and in summary, the radar operation can be taught as following. The synthesizer generates the chirp is transmitted, and the RX antennas, if there are multiple antennas, they receive a backscattered and delayed version of their chirp. The IF signal that comes out from the mixer consists of multiple bit frequency. Each bit frequency is proportional to the distance r of the corresponding target. The IF signal is filtered and digitized. Importantly, the ADC sampling should support the IF bandwidth of the slope 2 times the maximum distance over the speed of light, right? And an FFT is performed on the returns of the DSP for obtaining the range processing. After the range processing, one can perform a second FFT on the returns of the DSP for the velocity processing. Multiple antennas, as I previously mentioned, can then be used to estimate the angle of arrival by using simple physical formulations and by knowing the spacing of the antennas. Now that we are slightly more familiar with the radar's fundamental principles of operation, we will look at some literature's state-of-the-art examples that use radars on board of drones. Radars on boards of drones have already been used for performing radar odometry, radar inertial odometry, obstacle detections and tracking, swarm and flight formation, environmental monitoring and remote sensing, as well as above ground level measurements. On the right picture, you see a radar platform from Ali Safa et al. Integrated in a drone's platform. This drone platform contains two different radars, a 24 GHz radar with two receiving antenna and one transmitting antenna, and a multiple receiver and multiple transmitting antenna, 60 GHz radar. In the case of radar odometry is a technique that is used to estimate the relative motion of the UAV with respect to the environment by analyzing scans obtained by the onboard radar sensor. It is a two-step process in which there is the need to detect essential features from the radar scan first, and then secondly there is the need to track the scattered point in radar data that directly relates to the target objects over time. An important example of radar odometry is found in the paper from Antonio Fulvio Scannapieco et al., in which they demonstrate the use of an FMCW 24 GHz radar with a bandwidth of 1 GHz and a range resolution of 15 cm. They developed an end-to-end multiple target tracking strategy which exploits both radar range and bearing measurements provided by the radar. They implemented a two-dimensional odometry approach, and their main result shows real-time radar odometry capabilities with a standard deviation with error forward and cross-range direction smaller than 1.5 and 3 meters respectively. They perform field testings with corner reflectors placed in a field and used as targets. Radar inertial odometry refers to the fusion of radar data with IMU measurements to increase the robustness and precision of the motion estimation, for example by using an extended Kalman filter. An example of radar inertial odometry was presented by Eric Bequist et al. In the Transaction of Aerospace and Electronic Systems in 2016. The authors proposed a solution that simultaneously uses radar range compressed images and IMU concurrently. You can see the range compressed images on the right, which are nothing else than 1D FFT on each radar return. These range compressed images are then fed into a radar odometry pipeline that estimates the above ground level altitude together with the range and drift estimation. An extended Kalman filter fuses the estimation to obtain motion estimation. Interestingly, the radar odometry approach improves the navigation error experienced by the IMU alone. Furthermore, the error in measurement reduced between 4 to 5 times when using the radar odometry. Another example of radar inertial odometry was recently presented by Christopher Durr and Gert F. Trommer in iScenes 2021. They used a 60 GHz radar, an IMU, a single board computer and a camera on board of a lightweight drone. The author present a radar inertial odometry architecture based on a Manhattan word assumption in which the Manhattan word suggests that structure may be approximated by planar surfaces that are parallel to the three principal plane of our common orthogonal coordinate systems. Based on these assumptions and based on radar measurements characteristics, yaw-hiding can be accomplished in the indoor environment. The resulting odometry approach can estimate all IMU offsets, providing accurate state estimation for indoor datasets covering several hundreds of meters. The approach performed with accuracies comparable with state-of-the-art visual inertial odometry, but it is very interesting because they achieved this accuracy with much better processing times that runs even on an embedded computer on board of the drone and faster than real time. Another interesting function that can be performed by radar sensing on board of drone is obstacle detection and tracking. A notable example, very recent in literature, from Nikki Wessendorp et al. Showcase obstacle avoidance on board of micro-aerial vehicles using an FMCW radar. It was recently published in 2021. Here on the left you can see the radar platform they used. They used a 24 GHz radar with 2 receiving antenna and 1 transmitting antenna. They used onboard up-core 2 GB RAM computer that was performing Kalman filtering, FFT, velocity, obstacle detection, and estimating the MAV state. Interestingly, this work demonstrates the effectiveness of a standalone 24 GHz FMCW radar sensor for the purpose of sense and avoid. Here in the right picture you see 2 different targets and the sum of the trajectory that the drones would autonomously perform while avoiding the obstacle. A multi-target tracking and avoidance algorithm have been implemented on a MAV and tested on both 1 and 2 obstacles, showing that the MAV is successfully able to avoid them when solely relying on the radar sensor. This really demonstrates that the resilience of this sensor can be effective also when required, especially in situations of fog, low light condition, and etc. So obstacle avoidance, detection and tracking is an important function that can be carried on board with radar sensing technologies. Interesting, another very important function that can be performed by millimeter wave radar sensing is swarm and flight formation in drones. In this article presented by Brian B. Tierney and Christopher Rodenbeck in Radio Wave Symposium of 2019, they present a millimeter wave multiple input, multiple output MIMO radar that was capable of 3-dimensional sensing for application in the drone formation flight and obstacle avoidance. Very interesting, they designed a custom MIMO antenna optimized for the anticipated flight dynamics. They anticipated the 2-second sense and avoid window flight dynamics, and they designed the antenna based on that. In this picture you can see an example of their use case in which 2 drones were performing radar detection, peer tracking, with very good accuracy in terms of azimuthal angle and elevation angle degrees, showing that this is swarm formation and flight formation is possible using also 24 GHz radar lightweight with custom antenna. In addition to the function previously mentioned, environmental monitor and remote sensing was also performed directly on board of UAVs. One of these examples is provided by Stefan Dill et al. At the IEEE Radar Conference in 2019, in which they exploited they addressed the special concept of a SAR to detect buried mines. The SAR idea is by providing very high resolution images, it's possible to even identify man-made objects like landmines in the SAR image by the spatial radar cross-section distribution. They have used a 2 GHz radar with a range resolutions of only 4.6 centimeters. The concept they presented in this paper is very interesting because they used the drone to support both FMCW and stepped frequency mode with a frequency range from 0.5 to 3 GHz, which is with a sufficient power output and sensitivity for operational distance to the scene of more than 15 meters. They showcase the first experimental measurement result by range profiling and laboratory near-field of SAR measurement, confirming the functionality developed in the drone radar module. And here you can see a SAR image of the range and cross range, showing the relative intensity and the identification of buried mines in the field. The SAR concept also they introduce is very interesting, in which they have a mode of circular flight and a mode of standard linear flight, in which when they detect interesting targets, then they start the second mode of circular flight that they use to produce very high resolution SAR images. Another interesting function that can be performed by radars on board of drone is the above ground level measurement. And here in this paper from Autonomous Chapter and et al. Presented at the German Microwave Conference of 2019, they showed a 26 GHz low-cost, low-power radar that you can see a picture here, and a low-complexity pulse correlation radar for online altitude over ground estimation of an unmanned aerial vehicle, so a drone. And they showcase the measurement on difficult pavement like the one that you see here, in which we have very different steps, and they also show the difference among LiDAR and LiDAR measurement when there is vegetation above ground or not. The results from this paper show that the comparison of radar with a commercial low-cost LiDAR sensor in two different scenarios prove the functionality of the systems. Especially important in sparse vegetation, the radar sensor outperforms the LiDAR, since the radar still can track the ground, whereas the LiDAR measurement the distance from the vegetation. So as we know, certain radar frequency can actually penetrate, especially the 26 GHz frequency can actually penetrate vegetation and measure better the track the ground measurement. With this, we have seen many different functions that the radar can provide on board of the UAVs, and let me conclude with a single slide. In conclusion, what I think is that perceptions doesn't only require advanced sensors, but also requires advanced signal processing and artificial intelligence strategy. There is a lot of progress today in the system-on-chip radar systems, a lot of progress in the dimension of packaging antenna array designs. We are seeing a lot of progress in the integration of multi-channel radio frequency transceivers in the system-on-chip, endowed with high-performance analog to digital converters that can improve the bandwidth and the range resolution of the radars, and in signal processing algorithms that are now embedded in real-time low-power computing platforms. However, what we have seen also from this small survey is that there is still the need for improved onboard capabilities for detecting, tracking, and classifying multiple objects to fully unlock autonomous operation of small drones in cluttered environment. The examples that we have seen so far are limited to laboratory examples or very confined systems. There is the need of AI and real-time processing, and might be enabled by having deep learning accelerator directly embedded on board of the drones. In addition, we require novel sparse compute systems because the millimeter imaging radars, especially the SAR type of radar, will produce an incredible amount of data, and we will need to compute this data directly online on low power computing platform on board of drones. So still, this needs to be addressed in order to fully unlock autonomous operations of small UAVs. With this, I would like to thank you for your attention, and I will take questions now. Thank you.